Recording in progress.
Good morning. How are you all doing today? Good morning to you.
Fine.
Hello.
How are you feeling?
Pretty good.
Good.
Getting better every day. Just a little coughing once in a while, but not too bad. Well, it was good to get some rain yesterday. It was quite a downpour we had for a while. So,
Yeah, we got some thunder and everything.
oh, we didn't get that here. Just a fair amount of rain. Let me see, what does my rain gauge say? Oh, the backlight on it is not on, so I can't really read it. No, I can't make it out. It's back there on the wall. I don't know. It seemed like we got like, I don't know, quarter inch, half inch, something like that out of that. Anyway, so when we left off last time, I'd shown you how to crack one single hash by, what do you end up with? We had the hash in the file. Well, we had the hash on the command line, and then we're able to open up the rocku file, or at least a subset of it, and then go through each line of the rocku file, hash each one of those words, and then match it up against the hash that we're trying to crack. And then if we get a match, great, we're done. We just print out the matching word, and then we end the program at that point. If we're not done, if that didn't match, we would then move on to the next word in the file, hash it, and then check for a match. So that just repeats over and over again. And the assignment that I left you with was one in which you needed to crack a whole bunch of hashes, maybe 20 to 100 of them. And the thing there is the same idea, is you read in the hash that you want to crack, and then you go through the process of opening the rocku file, hashing each word, matching it against the one you're trying to crack, and then if it matches, great, you print it out, and then you move on to the next hash that you want to crack. The problem there is that if you want to crack a whole bunch of hashes, and the rocku file that you're using is large, like it's the one that holds 1 million entries, it can take a while to crack them all, because you have to do this scan through the rocku file, hashing each word as you go. And then once you crack the word, you excuse me, just trying to hold out as long as I could without coughing. Once you find the word, you start the process all over again. And so it can take maybe anywhere from 1 second to 5 seconds to crack each hash, because you have to repeat this process over and over again. And so the observation there is that we could speed things up a lot by doing a couple of really easy things. One is we end up hashing the words in the rocku file over and over again, but you know, every time we hash that word, it always comes out to be the same hash. You know, the hash of the word password is always exactly the same. So what if we hashed all of those words to begin with and stored them away so that we wouldn't have to hash them every single time? And the other thing we could do is, instead of opening that file for reading and then scanning through it, what if we loaded that file into memory so that we could have it all like at instant access in the memory versus on a disk file? The disk file is like probably on the order of 10,000 to 100,000 times slower than just accessing something in memory. So if we could load it all into memory ahead of time, we could speed things up a lot. So I think there's two things we could do. We could pre-hash all the words in the rocku file, and we could load that file into memory. And so that's what we're going to tackle over the next couple of days. So I think I wanted to start with that first suggestion. What if instead of hashing each of the ROCU words as we go, why don't we hash them all up front? And then we can write a program that will quickly crack a hash by just scanning through that file, looking for the hash, and then the plain text password is sitting there right next to it. So it's going to kind of leverage a couple of the programs that we've already written. But I think we're going to write them from scratch anyway, just to get the practice. So that's what we're going to tackle today. Today we're going to tackle, and I don't think it'll take that long, to write a program that will crack a whole bunch of hashes, or at least crack one hash. We'll just do one hash, but by scanning through the file of a pre-hashed ROCU file. And then maybe we'll do some timing on that, and we'll see which one is faster. Okay? All right, so let's switch over here. Oh, it's me. There we go, that's what we want. All right, so let's take a look at what we've got so far. This was the program we wrote last time. You give it a hash that you want to crack on the command line. And then it opens the ROCU file for reading, and then reads each line of that file, removes the new line, hashes that line, and then checks to see if that hash is the word that you want to crack. And if it is, it then prints it out, and then it exits the program. So that's our version that we wrote last time. And so we're going to take this version and just kind of rework it a bit so that it doesn't do this part right here over and over again. Okay, so I'm going to duplicate this. And let's rename it to, let's just call it crack hash 2. So I think the first thing we need to do is write a program that will go through our ROCU file and will hash it all, hash each one of those words, and then put the hash and the word itself into a new file. So let's kind of like write that one from scratch. Let's call this a pre-hash. That's what it's going to do. Let's see, we might need string, and we're certainly going to need MD5. There's our standard main setup. Okay, so what I'm intending to do here is we're going to give it the name of the file that we want to read from as the first command line argument, and the name of the file we want to write to as the second command line argument. So the first thing we should do is just check to make sure we've got enough command line arguments. So if argc is less than 3, we know we don't have enough. So we're going to print an error. That's too long of an error message. Must supply a source and destination file. And then we'll exit the program. Okay, next step would be to open up the first command line argument for reading and open up the second one for writing. So there's our input file, and we'll check to make sure we actually got it open. If we didn't get it open, then let's make a error message string, and we'll print into it can't open %s. Print out the error message, and then exit. Okay, that should take care of the input file. And now let's open the output file. Don't need quotes around that. And then check to make sure we got that one open.
So do we not care about closing the input file there just because the operating system takes care of it for us?
Oh, you know, we probably should. That would be a good thing to do. Right, you know, so if we weren't able to open the output file, we should close the input file before we exit. Is that what you're saying?
Yeah.
So at this point, we've got both of the files open. We've got the input file open, and we've got the output file open. Now we can start reading from the input file. We'll read from the input file, take that line, probably remove the newline character from it. And somebody brought up the other day that they found a couple of things online about how to remove the newline character, and there were a couple of variations on that. One of them was I think, was this. Okay, that was one variation on it, and the other one was this one. Okay, so there's this one here, and there's this one here. So the second one basically calculates the string length of the line, subtracts 1 from it, and then uses that as an index into the line string itself and changes that character to a null character. And the one above it uses the string character function to go find that newline character. And you know the string character function returns the pointer to where that newline character is. So it dereferences it and then stores the null character there. So both of these will work. But there's a reason why I wrote it this way. So can you figure out?
That first one will crash if there's no new line. It'll
Correct.
try to dereference null.
Yeah, so if there's no newline character, we'll get back a null from the string character function. And if we try to dereference a null, the program will crash. And then this one here, also, if there's no newline character, actually what it will do is it'll just take whatever character is at the end of the string, you just replace it by a null character. So if there's a newline character there, great, it'll do the right thing. If there's not a newline, if there's a newline character there, that's great, it'll do the right thing. If there's not a newline character there, it'll just overwrite whatever character that happens to be. So both of these examples here work great if there's a newline character at the end, but there is a slim chance that there isn't a newline character at the end, and that could happen up here. If the line that we're reading in is more than 100 characters long, it'll just stop at the 100th character, and there won't be a newline character sitting at the end. There will be a null sitting at the end, but there won't be a newline character there. So this way that I've written here takes that into account, that it should only replace the newline character if it's there. And if it's not there, it just does nothing. So just a little bit of a safety valve in there, just to avoid the problem of if there's not a newline character.
And that second one, if the length of the string is 0, the index would be -1. Would that cause a crash?
That is true, yeah. So if the line is like just nothing at all, yeah, that, I mean, it might not crash, but it certainly might cause a problem. Yeah. So these are the kinds of things you have to look out for, where they work 99.9% of the time, but it's that 0.1% that will cause a bug that would be really hard to track down. Okay, so let's get back to where we were. So we stripped off the newline character. Now we can go ahead and hash that string that we've got. And then we're going to print out the hash, and then maybe a space, and then the plain text word right next to it. And then finally, we'll free up the hash because we no longer need it. And then we'll move on and do the next one. And then when we're all done, close the input file, close the output file, and that should be it. So we'll go ahead and compile this unless you see something glaringly, obviously, that I missed.
Can you scroll down so I can see the rest of your code, please? Thank you.
Oh, I'm in the wrong directory. Okay, it compiled. And I ran it, so I gave it the input file, which is the Rocky 100 file, and then the output file, which is I called ry hash 100. And let's take a look at it. I think it looks reasonable. So one of the things to notice here is that the reason why I arranged it in that particular order, with the hash first and then the plaintext password second, is so that all the hashes nicely line up here on the left-hand side. We'll take advantage of that. The fact that those hashes nicely line up. If I had put the password first, then the hash would come second, and then we all be kind of like zigzagging around. And we wouldn't necessarily know where the hashes begin and where the hashes end because the passwords are different lengths. So we'll be able to take advantage of the fact that they are all the same length going down the left-hand side to make searching this a little bit easier. Okay, so there's our pre-hashed file, and we can do this for some of the other ones too, like we can do the 1 million file. Why not? How big is that file? My IDE froze while it loads that thing in. There it goes. Huh, it's huge. My ID's kind of frozen. I'm going to close this. Hopefully that'll... Oh no. Oh, there it goes. How big is this thing? It is, oh my goodness, 41 megabytes. So that's a large file. But nevertheless, it should all be there. Let's we can look at like the first 100 lines of it. Yeah, it looks okay. Okay, so let's go back to crack hash 2. And so this is one that's going to read in the hash we want to crack from the command line. It's then going to open up the rocku file, but we're going to use the one that's pre-hashed. We'll change the default one to be the ry hash 100. Open that file for reading. Then read in a line, right? But now this is 100 should still be enough for that for our purposes. Actually, let's go ahead and make this 1,000, just to make sure we got plenty of space. We're going to trim the new line, okay? And then we no longer need to do this because everything has already been hashed. So let's pluck this out of here. And now we want to check to see if the hash at the beginning of the line is equal to the hash that we're trying to crack. And the one that we're trying to crack is sitting here in argv1, but hash here does not, first of all, it's not a variable that exists anymore. We can't put line here because the line contains the hash and the plain text string. So there's a couple things we could do here. Do you see what the problem here is? That this is never going to be equal to each other, right? Because the hash we're trying to crack is just a bunch of hexadecimal characters. And the line contains that plus the plain text password. So these will never be equal to each other. So there's a couple things we can do here. One is we could split up that line into the hash and the password. And we could very easily do that with scanf, which could break up that line for us. But the other thing we could do is we could just tell the string compare function, don't look at the whole line, just look at the first 32 characters of the line. Stop there. Ignore everything after the 32nd character. So there's a version of string compare in which, first of all, it's called string n compare. You pass in the two things you want to compare, and you pass in how many characters you want to look at. Okay, so this is string compare, but it's only going to look at the first 32 characters of the line. Everything beyond that is going to be ignored. So if the first 32 characters of the line is equal to the string or the hash we want to compare, then we can go ahead and print out what we found. And we can just print out the entire line because it contains both things there. Okay, we don't need this anymore, and that should be it. Okay, so let's give this a try.
Well, we don't need MD5, right? Because we're not calling it anymore.
Oh, true. You're
And we
absolutely
don't
right.
need the
So we don't even need the
crypto.
include at the top, right?
And we don't need to link to the crypto library.
Now it's just all string compares, right?
Yeah.
Okay. All right. So let's find something to crack. What was one of the words we used last time? Zebra. Okay, so let's try to crack this. So let's do the original one. Oh, right. And the zebra is not even in the original 100 file, so we need to tell it to use the rocku 1,000,000 file. And then it found that. And then let's try that on crack hash 2. Oh, didn't find it. Because it's not in the rocku 1,000,000 file, it's in the ry hash 1,000,000 file. There we go. Found that. So they both seem to be pretty quick. Let's find a password that's like down near the bottom of the rocku 1,000,000 file. So it has to scan through the whole thing before it finds it. So let's look at like the last, I don't know, 100 lines of the rocku 1,000,000 file. I don't know. Let's just find this one right here. So we're going to try to crack this hash. So this is all the way down near the bottom of the file. And, you know, took a little while. Let's go ahead and time that.
Wait, that was not.
So that was the original program.
Oh, the original program. Sorry.
Yep, the original program. And it took about almost 1.5 seconds to do that. And then we'll try it with ry hash 1,000,000, and then we'll put in crack hash 2, and we'll see if this is faster. Did you see that?
A little bit. A little bit faster.
Just a little bit faster? Well, I mean, maybe that was a fluke. So we're looking at, what's this, 5/100th of a second, about what is that, 1/20th of a second to do this one versus almost 1.5 seconds for the previous one. And so, and the main difference between the two versions is just that, basically that MD5 line. The rest of it is pretty much the same. We're just doing string compares, and the strings we're comparing this time are longer than the ones we were doing before. No, I'm sorry, they're the same length. No, never mind. So the only thing we really took out was that MD5 function. And so it's that MD5 that's consuming most of the time in cracking this. So if we can pre-hash all the words that we want to crack, we can make it go a lot faster. What's the speed up here? 0.05 divided by 1.4. Nope, I want to go. Do I want to go the other way? So it's about 28 times faster. Any comments about that?
Not really. I mean, that's you pay the speed penalty once.
Right, in doing all the pre-hashing.
Right.
Right.
But
However, I wonder how this would work if we had to crack a whole bunch of hashes.
that was my thought. Yeah. I think the speed benefit's really going to add up there.
But if we had to crack a whole bunch of hashes, if we just kind of took what we've got now and wrote a program that would crack a whole bunch of hashes, we would still have to open up that ry hash file, scan through it, find the hash we were looking for, print out the one that we found, and then start the process all over again. So there would still be a bit of a penalty in having to open the file for reading every single time we wanted to crack a hash. Because basically, every time we crack a hash, we have to start over again, right? We have to start from the top again because we don't know where in the file that hash is going to be. It could be near the top, could be near the bottom. So we could speed things up yet again if we could load this entire file into memory. And then we would only incur the penalty of loading it in once, and then we could scan through that thing really fast, because scanning through something in memory is a lot faster than scanning through something that's in a disk file. But the problem here is we don't know how big that file is. There could be 100 entries, there could be 1,000,000 entries. We don't know ahead of time how big it's going to be. And so if we want to load this thing into memory, we need to know how much memory to set aside to hold this thing. And we don't know ahead of time. So our program is going to have to figure that out. Our program is going to have to basically figure out how much memory to set aside and then go ahead and do it. So one strategy we could do would be to maybe open the file for reading, count the number of lines in the file, and then that would tell us how many strings to set aside. So if we could count the number of lines, and let's say we came up with 100 lines, then we knew that we would have to set aside 100 lines of strings, but then how long do we make each one of these strings? We know it's going to have to be at least 32 characters long, right, enough to hold the hash, but then how much extra space do we set aside for the passwords? Now, we know for like the Rocky 100 file that none of the passwords are longer than like 20 characters. But if we are loading in a file where we don't know how long each one of those lines are, in that Rocky 1,000,000 file, they could be quite long. So maybe we could say, let's set aside 100 characters for each one of the strings. So we got 100 lines long and then 100 characters wide for the strings themselves. And now we have another problem. We know that the first 32 characters are going to be the hash. And then there's going to be like, passwords of different lengths here. Most of those passwords are only 8 characters long, somewhere in there, 6 to 8 characters long. So what happens to all this space over here? well, we end up kind of wasting that, right? 32 characters here, 6 to 8 characters on the average case for the password. So that's about 40 characters right there. And so we end up wasting actually about 60 characters per line. Now, we could make this shorter, but we still end up wasting space because we kind of have to make this width be the worst possible case, which is somewhere in that file there's a really long password, and we have to allocate space for that. We have to make sure there's enough space for that. But most of the passwords are going to be short, which means if we make this 100 characters wide, but we only need on the average case about 40 of them, that means we're using up what am I trying to say here? We're using up twice as much memory as we actually need. Am I making sense? Right? So it's not drawn to scale here, but if there's 32 characters here and 8 characters here, that's a total of 40 characters, which means there's 60 characters over here we're not using. And if that's the case for the entire file, that's roughly half the file is just blank wasted space. So this would be the case if we made a 2-dimensional file to hold this password. Either 100 lines, and each line was 100 characters long. So we would set that up by saying character, let's call this ry, and it's 100 lines long, and there's 100 characters per line. So a 2-dimensional array. But we'd end up wasting about half the space. Okay? So another strategy would be we could maybe, instead of counting the lines in the file, we could just find out how big the file is in the number of characters, and then just allocate one giant array, one giant string to hold the entire file. And then we could just pull the contents of the file straight in to that one giant string. So we could look to see the rock U100 file is 787 characters long. Oh, actually, it would not be that. It would be the ry100 file, ry#100 file. This one, 4,087 characters long. We could allocate 4,087 characters and then just pull the entire file into that. But there's a downside to that. They're now not broken up by line. They're just one giant string. So we're actually going to do kind of like a hybrid approach. I'm trying to decide what direction to go with this. We could do an approach where we pull the entire thing into one string, but then we figure out where each one of the lines begins. And then we keep a second data structure that keeps track of that. Actually, so I'm thinking, like, if we have time, I might actually show you 2 strategies for doing this. So here's what I'm thinking. Let's say we have a file that contains, I don't know, some foods in it, right? We got pizza and sushi and taco. What else?
Hot dog.
Hot dog. Okay, but we know the file doesn't actually look like this. Right? The file actually looks like pizza and then a new line and then sushi and then a new line, taco and then a new line, and then hot dog and then a new line. That's what the file actually looks like. So if we were to read this file into memory and just pull it all into one giant string, we would get this. Actually, it's not even a string. It's just an array of characters in this case. But then if we wanted to go to the third word in this file, we'd have really kind of no way of knowing where that word began. We would have to scan forward and basically count the new lines as we went. And when 2 new lines had gone by, we knew that was the beginning of the 3rd word. And if we wanted then to go back to the 2nd word, we'd have to start over again. Scan to the file, look for that new line character, and then the next character we know starts the 2nd line. So that's not a good strategy. So what we're going to do is we're going to build an array. Where each element of this array points to the beginning of one of these strings. Does that make sense? And so now, if we want to go to the 3rd word in the file, all we have to do is go to index number 2, zip over to that through that pointer, and then there it is. There's that 3rd word. If we want to go to the 2nd word, we just go to element number 1, follow that pointer, and there it is. So this gives us random access into the file, even though the file is not organized as itself an array of words. It's just an array of characters. Okay, so does that seem doable, or does that seem kind of overwhelming?
I think every programming assignment is overwhelming, but you just got to go at it one step at a time until it's not.
Well, how can we break this down into smaller, manageable pieces so it doesn't seem so overwhelming? So this is the data structure we're looking for here. Which of these pieces do you think we should tackle first?
Well, build that string.
Build which one?
The one on top.
The one on top? Okay.
Yeah, pizza.
Yeah. So to build this string here, let's break that down a little bit further. We know that the contents of this string are going to be the contents of the file. How do we know how long this should be?
Can you ask the operating system how long the file is?
Absolutely, we can. We can ask the operating system, how long are you? And so that is done with a function called stat, which I guess stands for status. Okay, so the function is called stat. We need to include this file here. And you pass it 2 things. Let's see if we can decipher what this is here. So here's the function called stat. There's other ones called fstat and lstat, but we're going to use just stat here. Can you tell me what you think this says here? Actually, just tackle the first one.
Well, it's a string with the file name.
Okay, good.
And it's restricted somehow, but...
So character pointer here, that's the important part. Character pointer tells you that this is a string, and path name, it means it's basically a file name. The const in front tells us that this function, stat, is not going to modify that string. So we could pass in a string and be sure that the string itself won't be modified. Okay, good. Now, second parameter. What do you make of this?
That looks like it makes something.
Okay.
A data structure, probably.
So, yeah. So this thing called this struct stat in front. So this is called a struct stat pointer. This is a data type that has 2 words, struct stat. So here's what a struct stat is. So you can kind of think of a struct as being similar to an object or a class in Java. A class is, a wrapper into which you can put things like you're making a class for a person. You can put in like their first name and last name and their age, their address. So you could put in all these different fields. But the difference between a class and a structure in Java and C is that a struct in C can only contain fields, whereas a class in Java can contain fields and methods. So that's the primary difference between the two of them. So this struct, called struct stat, it's actually 2 words, contains information about a file. And here is the type of the field, and here's the name of the field. So it contains things like, the ID number of the device containing the file, the inode number, which is the ID number of the file itself. We got the file type. But what's the thing we're looking for here? Which field is the thing that we're looking for? There's only one thing in here out of the 10 or so that are in here that are actually what we need. Do you see it? Let me zoom in a bit if you can't make it out.
In the chat, somebody said ST size.
Yes, that's the one we're looking for right there. Tells us the size of the file in bytes. So if we can make use of this, we could ask the operating system, how big is the file? And it will tell us in bytes. And that'll tell us how much memory we need to set aside for this. Okay, so let's do that. There's another comment here that another way you can find out is you could open the file for reading and then use a function called fseek that will basically move the pointer to the end of the file. And then you could ask the pointer, where are you in the file now? And it will tell you how long the length is. And it says that's more portable in that, it's not unique to a Linux file system. However, I believe stat is, yes, stat is what's called a POSIX function. POSIX is a standard that says that all Unix or Linux-like systems, whether it's Linux or Solaris or HP Unix, if they are going to be POSIX compliant, they must supply the functions defined by the POSIX standard. And so Unix or Linux operating systems are free to add any other functions that they need, as long as they provide, at the very least, the ones defined in that standard. And even other operating systems like Windows that aren't themselves Linux or Unix based, if they want to be POSIX compliant, they have to provide these functions as well. So is Windows POSIX compliant? And the quick answer is yes, it is. So that means even if you wrote this program and ran it on a Windows system, it would still work because the stat function call is there as well. So you're right. I suppose using fseek and ftell might be a little more portable if you're going to an operating system that isn't POSIX compliant, but as long as it is POSIX compliant, this should work. So I think this is going to be maybe kind of like a program where we just do some experiments and see what works and kind of learn how to do this process of reading a file in. Then when we actually get around to doing the real program, we'll be able to harvest like the individual components out of this. So it looks like we're going to need a header file called sysstat.h. All right, so let's see if we can break this problem down into the smaller pieces. We want to just accomplish this. Let's just get that file into one large array, and then we'll go from there. So the first step seems to be ask operating system for size of file. Once we have that, what can we do with that? What do you think the next kind of step would be?
Memory allocation.
Good. Okay, so that would give us this chunk of memory that would be exactly the right size. What next?
Maybe a for loop that copies characters individually from the file into the string.
Okay, and so just to take that a step backwards, we could say we just want to load that file into that chunk of memory, and then we'll figure out how to do that.
Okay.
So once we get to that point, once we've accomplished loading it into the memory, how could we then kind of verify that it's all there? Like, without touching anything inside of here, maybe we could look at a few random characters in there. And if we knew what the contents of the file were, we could then verify that, these characters are the right things. So let's go from there. Okay, so step number 1 is going to be ask OS for size of file. And then we're going to allocate memory. And then load file into memory. I kind of like writing down a little to-do list like that, just to remind me about what I need to do. So let's tackle these one at a time. We know the name of the file is going to be sitting in argv1. So let's see how we could use this. So we need to pass in the file name that we want to get the status of, and then pass in a pointer to struct stat. So here's what we're going to do. We're going to say stat argv1, which is the name of the file we want to get the status of, and then we need to pass in a structure. So we're going to go struct stat, and then we're going to call this, I don't know, file info. So this declares a variable called file info whose type is struct stat. It's going to be one of these things. So inside of that structure is going to be fields, one called stdev, one called stino, one called stmode, and one called stsize. The second parameter to stat then will be a pointer to that structure. So we just put an ampersand in front of it. And that's all we have to do. So we're going to declare one of these struct stats and then pass in a pointer to it. And then stat's going to fill in all of those fields for us. It's kind of like calling scanf. and putting ampersand in front of the variable we want scanf to fill in. So we're going to pass in a variable, pass in a pointer to it so that stat can fill it in. So let's just go ahead and print out the size of the file. The way you get access to the fields inside of a struct is almost identical to the way you get access to the fields inside of an object in Java. You just give it the name of the structure, and then a dot, and then the field. Okay? Is that easy? Right? So here's the name of the field right here, st size. And then you just give the name of the structure, a dot, and then name of the field.
So that field's type was, what was it? OFFT?
OFFT offset. So
Okay.
it's actually probably going to be.
Is that yeah? That's what I was thinking. Is that a long?
It's probably a long, because files could be bigger than 2 billion bytes. I think that's enough for now. Let's just see if it works. Let's give it a file that we know the size of, like this one right here. We know it's going to be 787. And it says 787. So we were able to ask the operating system, how big is that file? And it told us.
It worked for me in Windows too.
Good. POSIX compliant.
Yep. So far, the only thing that hasn't is the random function. That's where I had to move to Unix.
And Windows has got to have some equivalent.
Yeah, I didn't bother digging into it. I just went back to Thea or whatever.
There's one called rand, and there's one called random. You could try rand instead of random. Okay, we got the size of the file. Now we need to allocate memory. So we're going to call malloc. We're going to pass in that size, which is this one. That's going to be the number of bytes that we're going to set aside. And then what we get back is basically just a whole bunch of characters. All right, call malloc, tell it how many bytes to set aside, and then we get back a pointer to just an array of characters. And now we're going to load that file into memory. So we need to open it for reading, and then we'll figure out how to actually get it in to the memory. So let's go ahead and open this. In order to use p error and exit, we're going to need standard library. There's a question. Should we allocate memory using the times size of character. And that would actually, I guess, be more proper. However, we know the size of a character is just 1 byte. And we know how many bytes we want to set aside. It's 787. So that's why I didn't bother to do it this time, because we knew that whatever number this gave back, whatever number stat gave back, that was the number we were going to pass into malloc. There was no reason to make it any bigger than that. Okay, so now let's load it in memory. So there was a suggestion to load it in 1 character at a time. And we could do that. We could use a function like, there's one called fgets, file get character, and then we could just basically loop through that 1 character at a time. But we could actually do better than that. We can use a function that we haven't brought up before. I've briefly mentioned it. It's called fread. And the purpose of fread is to move bulk data out of a file and into memory. You basically tell it what file you want to read from and how many characters to read or how many bytes to read, and it just pulls them all in. Actually, passing 3 things. What file you want to read, how many characters to read in, and then where it's going to go into memory. And it just pulls them all in all at once. Let's take a look at fread. Okay, so fread, you pass it actually 4 things. You pass it the pointer to the block of memory, and then 2 numbers that tell it the size and bytes of each element to read and the number of elements to read. So we're going to pass in 1 for this number here because we're reading characters in, and then this is going to be that size of the file. So the reason why both of them are there is because fread could also be used for files that contain what are called records. Let's say you have a file that contains a bunch of integers. And I don't mean integers represented textually as characters. I mean like actual 32-bit integers. So if you have a file that contains, let's say, 100 integers, and each integer is 4 bytes long, you would pass in 4 here, and then 100 here. That's just kind of a convenience. So that you would pass in size of int here, and then the number of integers you wanted here. And then fread would just multiply them together and then pull in 400 bytes. That's all it's going to do. It's just going to take these 2 numbers and multiply them together. Okay, so, sorry, we pass in the block of memory where it's going to go, the size of each unit of data we're reading in from the file, how many of those we're going to be reading in, and then finally what file we want to get it from. So fread, where it's going to go, which was contents, the size of each element, which is a character, the number of characters, which is fileinfo.st size, and then where it's coming from, which is our input file. And then what fread will return to us is the number of characters that it actually read. It says right here, it returns the total number of elements successfully read. At this point, we're done with the file, so we could just close it. Now, we can't just print out the contents of the file because it's not a string. There's not a null character sitting at the end. All it did was it just pulled in the contents of the file, and the file itself does not contain a null character. It just contains characters and newlines. So we can't just print it out because there isn't a null character there. That's why I said we had to do something like just look at a few characters that are in there. So maybe we could look at the first character. Or the first few characters. Let's say %C, 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 %C. That's 4 of them. And anything else we could look at? Check to
Well,
see
you
if the
could look
number of
at-
red characters matches the size of the original file. That's probably
Right.
a good idea.
Didn't fread return a size t, not an int?
Oh, yeah, that's true. How about this? Got %LD. Oh, wait. But expected %LD. Okay. So the file size is 787. I printed out the first 4 bytes of the file, and they came out to be 1, 2, 3, 4, which are in fact the first 4 bytes of that file. If we do something like the food file, that's in a different directory. So let's do //food. There we go. We can see that the first 4 bytes are piz, and I know the first one is pizza. Let's take a look at it. It is right here. Pizza.
In our in my CS66 class, we use assert commands a lot for
Yeah.
C++ testing. Is there something like that for C, and would we want to use it?
There's a macro called assert. Well, let's give it a try. Include assert.h. So what can we do here? Now, so if this was the food file, we know that the first 4 bytes would be PIZZ. If they were any other file, this assert would fail.
Maybe he was suggesting use that for the fread instead of.
Oh.
No, I was pretty much thinking what was just typed, but
Okay.
yeah, that works too.
Did assert let you give a message if it comes out?
No, assert ends the program. And
But it
how we're using it in C++, we have to
Okay.
do
But it
exception catching if we want the program to continue to go.
But it doesn't tell you why.
It tells you what line the assert
Okay.
happened on, failure happened on.
Okay.
But there's no like assert with message or anything like that. Nope. the assert.h contains one contains one thing. Yeah. So the only problem with this is that if we change the file we're reading in, then the asserts are not going to work.
Right.
They're all going to fail. But at least it didn't bomb out right here. Okay, so it looks like this worked, right? We asked the operating system for the size of the file. We're able to allocate memory and then load the file into memory. But we don't have the ability to just quickly go to each one of these words within the file or each one of these lines in the file. So that would be our next step, would be build this thing here. So first of all, what is this thing here? I mean, it's obviously an array, right? But it's an array of what?
Pointers.
Right, the array of pointers, very good. Pointers to what? Whenever you declare a pointer, you have to tell it what it's pointing to. So what is this first one pointing to? I know it's pointing to the first word, but
Character.
yeah, it's pointing to a character. This is basically a string, right? This is basically saying, here's the beginning of a string. And this one here is also a pointer to a character. So this is an array of character pointers. Let that sink in for a moment. So this is an array of character pointers. And actually, we've seen that before. Have you seen an array of character pointers before?
argv, right?
Very good. Right here. That's an array of character pointers. So one way to declare this is, let's say we called this, I don't know, let's give it a name. Let's call it lines. We would say character pointer lines array. So it's an array of character pointers. But how many of them do we need? Like, if we're going to allocate space for this thing, we need to know how many of them to do.
Well, we'd have to count the new lines.
Yeah, we could count the newline characters in there. And that would tell us how many lines there are, how many strings are in there. Okay, so let's do that.
Now, I know you tend to drip feed us information and problems.
Mm-hmm.
And as we're working through problems, we're going to have a potential issue with the last line, right? It may not contain a new line. It might not contain a new line.
That is true. However, I've ensured that all the files you're going to deal with have a newline character on the end.
Okay.
The way I've done that here is, if you notice, at the very end, there's actually one blank line here.
Okay.
If I was to take away that, then this would just be Alexander, and there wouldn't be a newline character at the end.
Well, you could always, because you know where the last character is.
Mm-hmm.
So if you count all the new lines, then you can look at the last character and say if that's not a new line, then add 1 to the number of new lines.
But isn't our memory allocated exactly the amount we'd need? We need an extra character in our memory allocation.
No, we don't have to have a character. We could, because we're not pointing, we're not using that last character, but then we'd have a point at that string.
Okay.
Well, whoever said that a moment ago is actually on the right track. See, another problem we're going to have is, yeah, this is going to point to the beginning of the string, but where does that string end? Where's the null character that tells us where pizza ends?
There isn't one.
There isn't one. There isn't one anywhere in here. There might be one sitting over here off the end of the string, but there isn't one actually in the string. So although we have a pointer to the beginning of the string, we don't know where the string ends. So what if we took these newline characters and replaced them with nulls?
Okay. Then in that case, you would have to be guaranteed that there's a new line at the end.
Right. But you see what I'm doing here, first of all? If I replace all the newline characters with nulls, that means that each one of these strings now is just that individual word, and then it ends right at that null character, and the next one begins after that.
Right.
So we could zip through this file and replace all those newline characters with nulls. But you're right, that very last one there, we'd have to guarantee there was a newline character at the end in order to be able to replace it with a null. So what if there's not?
You would reallocate that string with one more character. Well, that
or what we could do is when we allocated memory for it here, we could just maybe add one more, just as kind of a safety net.
Sure. It's only one character.
Or we could say, maybe let's not worry about it for now. We'll fix that bug if we come to it.
Let the next person figure it out.
I'm thinking, like, in the interest of time right now, let's not worry about that one for now. But you're right, that is something that we should definitely consider. And we could partially fix that problem by just adding 1 to this. So we always were guaranteed there's at least one more character at the end of the string, room for that null character. And then we'd have to do some kind of thing to say, like, well, if we got to the end and we didn't see a newline character, then go ahead and put a null at the end. Right? So there's a little bit of extra work we would have to do. But let's see what we can do here. If we can count the lines by counting the number of new lines. Okay, so all we have to do is just loop through this giant array and count the new lines as we go. And I'm getting tired of typing in fileinfo.st_size. So I'm just going to make a new variable. Let's call it file size.
It has to be longer than int, right?
Oh, yeah. Find all the places where this is. So while I'm doing this, I like, someone commented like, I like to dribble in stuff, right? Because I'm all about what's called just-in-time teaching, which is rather than doing this data dump on you and saying like, here's everything you're going to need to know for this assignment, and then you have to sift through all of that stuff to figure out what I actually need to know. What I like to do, and what has worked out well for me, and what I've been taught by other teachers, is give students just enough information to be able to start scaffolding up what they need, and then they hit a ceiling where they're like, I can't figure out how to do the next step, and then that's where you say like, okay, here's how you do that, because now your mind is ready to receive that information because you realize that you've hit a roadblock. What I hated doing as a student is like, here, like I said, like here's all the information you might need plus some extra stuff. Like here are the 18 ways to read a file in. And then your assignment is to read a file into memory. And you're like, well, which one do I need to use of those 18 ways? And I think there's some students get into like, what is it called? Like decision paralysis. We're like, I don't know how to evaluate which one's the best one. So I prefer kind of like you said, just dribble out the information. You realize that there's an obstacle in front of you, and then I tell you how to get past that obstacle. Or we figure out how can we get past that obstacle without learning anything new.
I know. I clearly see this playing out time and time again in the lectures, and I think it's such a great way to learn the information because you get time to think.
Yeah.
And approach problems.
And I think time to be creative because I might say like, well, how can we figure out how many lines there are? And someone said like, well, let's just count the new lines, and we don't have to know anything new, right? We can use the tools we already have to do that. Maybe there is another way to do it, but I like the idea of making use of what we already know and taking that as far as we can until we really hit some kind of roadblock that we just can't get past. So we're going to loop from 0 up to the file size, and then every time we hit a newline character, we're just going to bump up that NL count by 1.
While we're in that loop doing that, could we also set that to the null character, or will that mess us up?
I like that idea, right? So while we're doing that loop, while we're counting those new lines, we could be changing them to the null characters as we go. Here's an example of where I indented this and then stuck a line in below it and didn't put the braces in. What would have happened? First of all, would it compile? Would it compile?
Sure, it'll compile. And then when you try to set content sub I to 0, it would be the character beyond the first character beyond the string.
Oh, not only that. This would replace every character.
Oh, right, because it's in that for loop.
Yeah.
Oh, yeah.
But it's not within the if.
Right.
Right. So to the compiler.
Yeah, sorry, I was thinking it was outside the for loop, but yeah, it's outside. Yeah, so just change the string to all nulls.
Yeah.
Nice.
And it wouldn't complain. It would just do it. Great. So let's print that out here. Number of lines. And let's give this program
Oh, again,
a
that
whirl.
for loop I should be size T, not in, right?
Now notice when I compiled it, it didn't really complain.
Right. It doesn't care unless you have a file that's bigger than, what, 2 gigabytes?
Yeah. Okay, does that seem reasonable? 6 lines in that file? One, two, three, four, five, 6.
There you go.
Okay. Well, I got a question for you at this point. It's almost 11 o'clock. Now, normally we would go to 12 today if we were talking about an assignment, but I kind of wanted to see if we could finish this piece here. But do you need to take a little break at this point? Go and grab a cup of coffee, go and grab...
I wouldn't mind stretching my legs.
Yeah, stretch your legs. So why don't we go ahead and do that? So we'll be back in about 10 minutes or so, 5 or 10 minutes. And then we should be done. I think we should be done by 11:30 or so. I don't think there's much left to do here.
Recording stopped.
Okay, let's see if I can catch up on some of these comments here. There was a comment that said, please explain the 12th class, 13th chapter, last topic. I don't remember what that was. 13th chapter? So you'll have to explain a bit more. And then another comment, allocate the +1 byte, and then just put a null there. Oh, okay. I kind of like that suggestion. So allocate the 1 extra byte, and then just put a null there, regardless of what happens to be there, regardless of whether there's a new line there or not. Then you need no special logic to handle the lack of a trailing new line.
Yeah, that's not bad.
Yeah, I kind of like that. That would be easy to do. Right? That would just be like put that +1 in there, and then 1 assignment statement to just stick a null character at the very end. Yeah, we'll go ahead and do that when we come back from the break.
I've got a question.
Yeah.
So in Windows, I was messing around with reading files, and I noticed if I don't use R or B for read binary, that it does some weird things. I noticed it was inserting a byte 0D and hex into my file, and I noticed in ASCII that's carriage return.
All right.
So I'm just curious if you could explain what a carriage return is, possibly.
Yeah. So this is actually a really good question. I don't know if we want the music going while I'm answering this. So different operating systems have different ways of indicating the end of the line in a text file. So a little bit of history here. Long time ago, there were actually 3 major operating systems. These days, we're now in a duopoly where there's only 2 major operating systems, but there used to be a third one. So there was Windows, or DOS, I should say. It's been around forever. There was Unix systems, and then there was the old Mac operating system back in the 80s and 90s. That Mac operating system is now gone, has been replaced by the Unix-like system that we have now. So in old Unix systems, ends of lines were marked by ASCII character 10, which is, now, I guess I should jump back a little bit further back than that. In old teletypes, or think about an old typewriter, if you can picture one of those things, an old typewriter where you have the hammers that are hitting the platen, hitting the paper, and then this platen that's moving back and forth, right? So the hammers are hitting and this platen is moving. And so when it gets all the way to one side, then you have to do two things in order to move to the next line. First, you have to move the carriage back to the left-hand side, and then you also have to roll it by one line, so you go to the next line. And those are two separate actions in a printer, in an old-style printer. Moving the print head over to the left-hand side, and then moving the paper down by one. And so the act of moving the carriage, or the print head, over to the left-hand side is called a carriage return. And then the act of moving to the next line on the piece of paper is called a line feed. Does that make sense? So it's like two separate motors have to be engaged to get a printer to do that. You got one motor that has to move the carriage to the left-hand side, and another motor that has to move the paper down by one line. And so there were two characters that were sent to make that motion. A line feed to move to the next line, and a carriage return to move it over to the left-hand side. And so on DOS systems, DOS-based systems, which includes Windows, text files have those two characters in there. Every line in a text file is marked by the end of the line by those two characters, a carriage return and then a line feed. But Linux and Unix-based systems, for whatever reason, decided to just use a single line feed character. And then when the text file actually comes out of the printer driver program will see that one line feed character and turn it into a line feed carriage return combination.
Oh, okay.
So
Right.
on the old, I used those old telex machines as a kid working in the library. And so if you punched in some text into a paper tape and played back the paper tape, you had to do carriage return first and then line feed. Because if you did line feed first and then carriage return, and then there were characters after that, the characters would start printing before the carriage got back to the left. So you get these random characters printed across the page as the carriage return was moving its way back to the left.
Interesting.
You had to do them in order.
And so it's because the carriage return takes time, the characters continue to be fed to the printer, and so the printer is just forced to just print them as they come, even if it's doing this motion.
Yep.
How interesting. So it couldn't even pause it and say, just a moment here, I'm still busy.
No, because that paper tape goes at the speed the paper tape goes. And so there's no memory for the characters. It just has to print the character when it sees it from the tape.
Interesting.
Yeah.
Right. So on Unix systems, that single line feed character is the end of line marker for a text file, and then the printer driver will translate that into the sequence of characters that are needed to actually do the right thing. And then the old Mac operating system, again for whatever reason, decided that just a single carriage return character was going to be the end of line marker. And then same thing, it would just translate it into the characters it would actually need. But the old Mac operating system has gone away, and what we're left with is two representations for text files, the Unix style and the DOS or Windows style. And some text editors will actually tell you at the bottom, sort of the bottom, which one it's using. And ours does too, right here. Right at the bottom. It says, this is a line feed. Oops, you don't see what I'm looking at here. Right here. You see that? This is a line feed separated file. And I think if we click on it, no. If we were to upload a Windows style text file, this would probably say CRLF, which means this is a carriage return line feed text file. Have you ever loaded a I guess we can. We can change what end of line sequence we're using. Have you ever loaded a Unix text file into Notepad on Windows? Remember Windows?
I did it the other way around, and I noticed there was some, I forgot what it was, but there's something odd about it where they didn't read right.
So if you bring a Windows text file into a Linux system, then it goes, what are these character returns doing here? And it just prints like a little funny character there. Like maybe a little question mark or a little X or something like that. But if you bring a Linux or Unix text file into Notepad, which doesn't understand anything but the DOS line ending style, then you end up with the file being in kind of like this stair step, where one line appears, and the next line, instead of going to the left-hand side, just simply goes down one line and then continues from there. So the lines go like this little stair step. And so that's why I always tell people, if you're going to edit a text file, don't use Notepad, right? It's really dumb. Use like Notepad++ at least on a Windows system, which understands the two kinds of text files.
It was weird for me as I was reading actually the raw bytes in, and I made a little program to swap them from like big to little endian, where it like flips the bytes around.
Yeah.
And for some reason, without doing that RB, it just insert some random 0D bytes in there in Windows.
That 0D are those carriage returns.
Yeah, but it's not actually a text file I'm reading from, so that's why I'm still a little puzzled why I was getting those.
So when you open a file for R, then it assumes that you're reading in a text file.
Oh, that makes sense.
And we'll do those translations for you. So by opening it as RB, you're saying this is a binary file. It's not a text file. Read in the bytes as they are, with no weird translation happening.
But Linux doesn't care, right? R and RB are basically the same in Linux.
Yeah. Because in Linux, there's only one character ending a line. In Windows, there's two characters. Although I'm wondering, I actually don't know the answer to this. If you open a Windows text file using R mode on a Linux system, will it do the right thing and turn the two character sequences into one? I suppose we could find out, but we would need a Windows text file to work with.
Yeah, I could try it on I'm using Windows primarily, but I have a Raspberry Pis and the Thea system, so I kind of bounce back and forth between the Linux and Windows.
Someone on YouTube says, nope, it won't do that. If you open a Windows text file on a Linux system using just R mode, will it translate the two character sequences into one character? And Victor says, no. But it's something that would be relatively easy to try.
Recording in progress.
Okay. So there was a suggestion while we were on the break that what we could do to handle this situation of the last line not containing a newline character, and this was a really good suggestion, was just go ahead and allocate one extra byte right here. Just go ahead and allocate one extra byte, which will guarantee we've always got one extra character on the end of our string. And then after loading the file into memory, which is right here, just go ahead and put a null character at the very end, regardless of what happens to be there. So if there was a newline character sitting there, we'll replace it with a null. And if there was not a newline character sitting there, we'll put a null there, and then it will work. The only problem that I can see with this is that if we do that right here on the screen, is that the last newline will be replaced by a null, and then when we count our newline characters, we won't have the correct answer. So we probably shouldn't do this until we have counted all the newlines. here. And then we'll just go ahead and append null character to end of array in case there was no new line.
I messed up the top. Did you, because that assert statement.
That should still be okay.
But if the, okay.
Because
so if we add
the amount of memory we set aside.
Sorry, yeah, so we're using file size. Okay.
Yeah, the amount of memory we're setting aside is going to be one character bigger, but we're still going to read in the whole file.
Okay.
Now, I'm not going to put a +1 here because remember the last index of this array is going to be file size -1. So if I add 1 to that, that'll actually go off the end. Okay, so let's go back to this here. So we figured out that this is an array of character pointers, and now we know how many there should be because we've counted up the new lines, and that'll correspond with how many strings we have. So here we've got 4 strings, which means we need to set aside 4 array elements here. So the next question is, how do we do that? How do we make an array of 4 character pointers? What are you thinking? Let's call this X, or N. Make an array of N character pointers.
So if we were doing an array of characters, we'd say char variable name and an array, array size. So would we just say char pointer name array size? No, wait. Yeah.
Yeah, so we're making an array called ARR of N characters. But you're right, we want to make an array of N character pointers.
Character pointers.
So yeah, it is just as simple as putting a star there. But this would make a local array, one that wouldn't stick around. So we should turn this into a malloc. If I wanted to make an array of N integers, I would do it like that. So what would be an equivalent malloc for this? So it would be
malloc
N
times size of int.
Size of int. And then assign that to
array.
But what type of thing is array?
Array is it an int pointer?
Yeah. Okay, so array is a pointer to an integer. It points to the first integer in the array. And then we have n of them, and each one of those boxes is the size of an integer. And I think we might also be able to do int array like this. But you don't see that as often as this one up here. Okay, so if that's how you make an array of n integers and turn it to an equivalent malloc, and what I wanted to show you here was this n goes right there, this int goes right there, and it also goes right there, and then this variable name goes there. And the only thing we add on is this star. See how that recipe works? So you take the type, and it goes here as the argument to size of, and it also goes out front here as the type of thing that we're making a pointer to. The name of the variable goes right here, and the number of elements goes right there. All you have to add on is this star to say that this variable here points to this array. Are we good?
Sure.
So let's turn this into the equivalent malloc. Let's use the same recipe. So here's our n. That goes right there. Times size of, and then what goes inside here?
Char pointer.
Yeah, it needs to be this thing, the thing that's sitting out in front of the variable name. That goes inside there. Good so far? Now let's tackle the front side. So the name of the variable goes out front. And then what goes in front of that?
Char pointer pointer.
Very good. Remember, the recipe says just stick a star out in front of whatever that is. So whatever that is just character pointer. So we're going to put that in front. And then add another star. Okay, so we're saying that ARR is a pointer to a character pointer. And that's what this is going to be, right? Lines here is going to end up pointing to this array. So this thing points to this thing. And this thing points to that thing, right? So we've got a pointer to a pointer. So when you're using like malloc, I mean, I think you can still use the bracket notation, but it's more common to just see stars in front of there because that's what it's really returning to you. It's just returning an address. It's not returning a whole array. It's just returning an address to you. So character, pointer, pointer, lines equals malloc. Number of new lines times size of character pointer. Okay, and that'll give us, well, it'll give us most of this picture. It'll give us lines that's pointing to this thing here. This thing now is a box that contains a bunch of small boxes, and each one of those small boxes is going to contain a character pointer, but those character pointers haven't been filled in yet. But we do have this larger box, and there's now null characters sitting there. Okay, so this is what we're aiming towards, but we don't quite have that yet. So now what we need to do is make one last pass through that array and find the beginnings of all those strings and assign them to each one of the elements of this array. All right, so to do that, we're going to scan through this thing here, and every time we find one of these null characters, we know that the very next character is going to be the beginning of one of these strings. So we'll scan through here, find a null character. When we find one, the very next one is going to be the beginning of one of these strings. Then scan through again, find a null character. The next one will be the beginning of a string. The only thing we got to do is make sure we don't do that to the very last one. And then the first one also has to be handled differently because there's nothing in front of that. So we can do lines 0 equals the address of the 0th character of our contents array. Okay, the 0th character of our contents array, the address of that is going to be what we store away in the 0th box of the lines array. Okay, do you see the picture again? This is contents, and it points to this whole box. Lines points to this smaller box. The 0th element of that is going to be the 0th element is going to get the address of the 0th element of this contents array. That's going to be the very first string. And you know, just to verify that that works, let's just go ahead and print that out. It's a string. And there it is. It printed out pizza, the first string in that file. You know what? I'll bet you if I do this, if I do lines 1 equals the address of contents 6, which I know is the beginning of sushi.
You'll get a compilation error.
There we go. There's pizza and sushi. So I'm not copying the string anywhere. I'm just pointing to the beginning of each one of these strings within that big, large string. Does that make sense? Right? The reason it's printing out pizza here is not because I made a copy of that string. It's because I'm pointing to it right here. And the reason I printed out sushi next is because this one is pointing right there. Now, the only reason I knew that was 6 is because I just manually counted it. I visually counted 6 characters in and knew that's where sushi counted. What we need is a loop that'll do this for us automatically. So we can go for int I equals, now let's start at character number 1. So we don't do 0 all over again. And then we'll go less than file size. And then we'll say if contents I is equal to the null character, then we know the very next character must be the beginning of another string. And then we just put an address in front of it. Okay, but I left this blank here because we have to put some kind of counter there. We can't use I because I is counting by character. We need another variable that counts by line. I don't know, let's call it, I don't want to call it L because it looks like kind of like a 1.
Line number.
Okay.
Too many equal signs.
Okay, so I've got I, which is counting character by character through the array, and I've got line number that's only counting up every time we encounter one of those nulls. So they're not going entirely in lockstep, but they are incrementing as we go through. And I think that'll do it. There we go, pizza, sushi. Now instead of just printing out 2 of them, let's go for int I equals 0, I is less than line num. Pizza, sushi, pickles, ice cream, granola, pasta, and 1 extra 1. Why did that happen?
Did we stick an extra null at the end of the string? I forget if
Well, we did. We did it right there.
Yeah.
But we're only going up to, but not including file size, so we shouldn't actually be looking at that one.
Oh, right.
Is it that I plus 1?
Oh.
Or we always look at the next character? Or element, rather.
But if the ith character is a null...
Now, is it because of the line num plus plus comes after? Because it's already 1. So if there really was only 1, okay. If there was only 1, then line num would end up being 2. So if it was just pizza.
So Victor said, this needs to be a +1 here. But the reason why I didn't put a +1 here was because that would go off the end of the array.
So how about before? No.
No, I think it does have to do with that line num plus plus, because it always that keeps track of where our next line number is, right? And then our print statement
You're
goes.
talking about this right here? Or you're talking about...
That's what Steve was saying, yeah.
Is it just a matter of line num just contains too many, and we should we should not increment this if, let's see, we started out at 1.
I think we can adjust our for loop at the end to go up to line num -1, maybe. If line num is going to be one step ahead.
It would be nice if this contained just like the number of lines, right? It should be, in this case, should be 6.
Right, so it's 0 through 5.
Yeah.
Oh,
so
but
this should be 6.
So line num is winding up 7?
Yeah.
So what if we said before that for loop, if this might just wind up doing the same thing, but before the for loop, initialize line number to 0. And then, I don't think this is going to work, but then where you have lines sub line num, no, wait, do pre-increment in line sub line num on line 72. If you do plus plus line num and then delete that next line. I don't.
Seemed to work.
Yeah.
So but in that case, no, it'll always. How did that change things?
Yeah,
So
good question.
that's the right number of lines, and that's the right numbering. Let's do this. Let's go into food. Let's take out that new line. Right? So it lost the last one.
Okay.
Well, that'll be something to think about there, maybe between now and next time. How do we fix that? Maybe I'll leave you with that. Fix that problem. So all you need to do to debug this is a line that has a new line at the end and a file that doesn't have the new line at the end. And make sure it can accommodate both. I don't know, maybe you can do something like after you read the file in, look at the very last character and see if it's a new line. And if it's not, then go ahead and put that null on the, in the next one. But then you still got a problem where you're not counting them correctly.
Right.
Maybe what you should do is, if there's not a new line character there, put one there.
Yeah.
And then make your sweep through, replacing new lines with nulls.
Yeah, I think, yeah.
Anyway, give that a whirl.
Kind of what I was thinking before, where, that would be easier. What I was thinking before is you just go through and count all the, oh no, that wouldn't, okay, sorry, never mind.
So between now and Monday, try that, figure out some way to get the number of lines to be correct and for there to be a null at the end of every line. And then where we're going to go from here is once we're able to load a file into memory, we could then load in that pre-hashed file into memory and then very quickly search through those strings for the hash that we're trying to crack. It wouldn't speed things up for cracking one hash, but the hope is that it will speed things up for cracking multiple hashes, because now we don't have to open that file for reading every time we want to crack one of the hashes. Everything's already in memory. We'll pay that price once to load it all in, and then we can scan through there really quickly. So that would be the next step. And then the final step after that would be, is there a faster way we could scan through that file instead of starting at the beginning and going towards the end? And even if it's all loaded in memory, is there a way we could scan through that array faster? And we could, if we could put the array into some kind of order. Let's say we sorted the array. If we sorted the array and then we're looking for a hash that starts with, let's say, a 0, then we know that's going to be towards the beginning of the array. And if we're looking for a hash that starts with F, we know it's going to be near towards the end of the array. So we could actually speed up our searching by kind of cutting down on where we search through the array if we sorted it. And actually, if we sorted it, we can do an intelligent searching algorithm called a binary search. So that's ultimately where we're going to end up, is we're going to load the entire array into memory, sort it, and then we can search it really fast using binary search. We'll pay an upfront price of loading it into memory. It'll take a few seconds to do that. In the case of the 1 million, actually we'll have a 3 million file by the time we get to there. For the 3 million file, it'll take anywhere between 30 seconds and a minute to load it in. But then cracking the hashes comes almost instantly. And so that's where we're going to end up. Okay, so between now and Monday, first of all, you got one program to write, which is cracking a whole bunch of hashes by just loading in a file over and over again. And the second one is going to be, see if you can solve this problem. And if you look online, you'll see there's another assignment called loading the dictionary into memory. And it's essentially doing what we just did today, is writing a program that can load the rocku file into memory and build this data structure that I've shown you on the screen here. Build this data structure right here. So you should now have enough information to be able to do that, or at least make your first steps into doing that. I think I gave you a template program, but let's see if you can just kind of like do what you have now. Read that file into memory, replace all the new lines with null characters, count up the new lines as you go, and then build that second array and fill that in with those pointers. And once you've got that, you've got this data structure right here that will give us quick, easy, random access to any string in that file really quickly. And then next week, we'll learn how to sort it and search it. I'm kind of excited about this. This project has gone in a slightly different direction than it normally goes in. Normally we I haven't talked about this whole pre-hashing thing at this earliest stage. So it's kind of exciting we're doing this. But not only that, we'll learn about structs ourselves. So we'll learn how to break up the hashes and the passwords into a struct, and then we can sort those structs really, really fast. So that's where we're going with this. Okay?
So for fixing this program, are you going to put that somewhere for us to work from that, or do you want us to just write it from scratch?
Well, kind of the whole point was I mean, the guts of this program become the main contents of the next assignment, which is loading the dictionary in.
Okay.
It'd be nice if you kind of like wrote it yourself so that you kind of get I mean, to me, when I copy and paste code, I don't necessarily like to just blindly copy and paste it. I like to type it in if it's something new. That way, as I'm doing it, I'm looking at every single word, every single symbol that goes down, and I'm like processing in my head what this line of code is doing. So what
no, that's fine. I just wasn't sure which way we were going.
So what I can do is we'll just take kind of like a scroll through it. And then when you watch the video, you can pause it and get the whole thing. And it'll be interesting to learn on Monday what you did to get this to work. mean, as it is right now, it works fine if there's a new line on the end. What we're trying to fix is, what if there's not a new line on the end? Yeah, that's it. That's the whole thing. Okay, and there was comment here like is what am I looking for here? Is it a matter of preference about putting spaces around the star? And the compiler doesn't care where you put the spaces. No spaces, spaces, it's all the same. So it becomes kind of a matter of user preference. I think a lot of people are going to, like when they declare a character pointer, they'll not put a space in front of the star, behind the star and in front of the variable, like I've got here. You'll see it like this. Other people will put a space there, right, to reinforce that it's a character pointer that contents is. And I'll tell you the reason why I think a lot of people will prefer not to put a space there. And this is it's a little bit esoteric, but it has a lot to do about the way the compiler interprets your code. So what if we have this declaration, like int x comma y? What type of variable is x and what type of variable is y? This is easy.
They're just both ints.
They're both integers, right? X is an integer, y is an integer. What type of variable are x and y?
Oh, x is an integer pointer and y is an integer?
Yeah. X is an integer pointer and y is just an integer. See, the star here is not a modifier of the int type. It's a modifier of the variable type. So by putting a space here, it kind of suggests that both x and y are integer pointers, but they're not. X is an integer pointer, and y is just an integer, because the star modifies the x. It doesn't modify the int. Okay, and that actually differs from the way Java kind of does things. Like if I have int array x comma y, now both x and y are integer arrays. It's not x is an integer array and y is just an integer.
So on that line 9, now 10, if you put int star space x comma y.
It makes no difference in
Now,
the compiler.
And if you get rid of the space before the star, that's still x is an integer pointer.
Yep.
And y is an integer.
Yep.
Okay.
So if you want to make both of them be integer pointers, you got to do it like this: int star x star y. Crazy, huh?
Yeah.
So that's why you'll see a lot of C programmers put the star next to the variable to indicate that that star is a modifier of the variable, not of the type. We had a question here was, will this program work if there's two newline characters right next to each other in the text file? Well, if that's going to happen, what you'll end up with is just one line that doesn't have anything in it. And that's fine, because now it's kind of like you intended for there to be a blank line there, like you have paragraph separators. So I would say the program will work, and it will work as designed, which was you'll end up with one line that has no characters on it. If you wanted to do something like, if there's multiple newline characters next to each other and just treat them as though there's one, then you'll have to do some special handling on that. Any other questions?
I don't think so.
All right, so I guess really quickly, let's take a look at we are way down here, loading the dictionary. All right, so I did give you a starter file here. Yeah, okay. All right, so you're going to start with that starter file. So here's the address. And then dictionary.c and dictionary.h include the code for loading the dictionary. You have to fill that in. I gave you a few text files. And then it shows you, here's the data structure we're going to build. Okay, there's some stuff in here about expanding the array. You don't have to worry about that. I mean, I showed you how to do it here, where you just have to count the number of new lines. What I'll probably end up showing you next time is how can we avoid that? How can we avoid counting the new lines as we go through in one pass? How can we make it so that we could expand the array as we go? And I'll show that to you next time. But right now, just load the dictionary using the techniques that we've got now. And then I gave you some code to search the dictionary. Looks like that's already written for you. And then some text files contain just some fruits. First 100 lines of the Rocky file. First 1,000 lines? Yeah. All right. So that's where we left off. Sounds good?
Okay.
All right. Well, have a great weekend.
You too.
And I'll be interested to see what you come up with on Monday to solve this problem. Take care, everyone.
All right.
Office hours after this, right?
I would be glad to meet with you.
All right, cool.
Talk to you later. Bye-bye.
Okay. Bye.
Recording.
And YouTube folks, same thing. I got to take off. C++ programmers will tell you that only int star is correct, and you should only declare a single variable per line to avoid the problem you described. Yeah. But, you know, if you have to, like, change your style just to avoid a problem, I don't know. Maybe Maybe there's something wrong with the language then. Anyway, yeah, so I got to take off. It was great having you. Go ahead and work on that problem over the weekend, and then come back on Monday. We'll see what you came up with to solve the problem of the new line or not new line on the last line of the file. Take care, everyone. Good to see you. Be safe. Get some sleep. Talk to you later. Bye-bye.